Okay.
My talk in a word, and I'm not a native speaker, so if there are any native speakers present, please tell me afterwards whether unordering is a meaningful word. Yeah, but I want to capture that the idea that this destruction, removal of an electronic order can happen coherently or incoherently, or both. And if I use the term disordering always sounds to me like very incoherent. Yeah, so maybe afterwards. So, and then I should qualify also electronic. I've spent a lot of my career on charge density waves, and these are combined electronic lattice orders. Yeah? So electronic order has a lattice component to it, which is meaningful because electron-phonon coupling, I guess, is finite in every material. And then I'm very happy to be here after 2 years. So because this was my experience from 2 years ago. What a beautiful first day. Looks like this week. And then what happened to me on the day 2 was this. So I got my one and only COVID infection here in Corsica. And then there was another thing happening, and this was day 4, where we had this thunderstorm coming, and after this, there was a complete power failure. So all of electricity was gone, not just this Wi-Fi internet for a couple of hours, which we experienced today. And then I don't know. There were definitely flashlights, yeah, and I could observe it from my room in the quarantine above this terrace where we get our foods. And here, was then how people tried to give their talks at the blackboard without presentation. And this is the guy who decided to go climbing instead of listening to my talk. Yeah, so. This is Luca, yeah, okay. Anyway, so I'm from Kiel. Kiel is in the north of Germany. It's on the Baltic Sea. People say it's beautifully located. It's not a beautiful city, but it's on the fjord, on the Baltic Sea. I'm a spokesperson of this so-called KINSIS, Kiel Nanosurface and Interface Science, where we combine physics, chemistry, life medical science, and engineering. About 140 PIs also working in this field. And then I'm a quantum person, so my very function is delocalized between Kiel and Hamburg. At DESY, I spend about 50% of my time also at DESY in Hamburg, which is this research laboratory where we have these super powerful X-ray sources, storage rings, Petra 3 for soft X-ray spectroscopy, as well as the free electron lasers FLASH and European XFEL for ultrafast spectroscopy. And there is a common institution between Kiel University and DESY, and this is this Ruprecht Hensel laboratory. So I'm an experimentalist, I should say right from the beginning. Okay, and this is what we do. We do soft X-ray spectroscopy of quantum materials. We cover the entire, let's say, innovation pipeline of quantum materials physics. So we grow our own samples, these layered transition metal dichalcogenides in particular. We build fancy instruments, photoelectron spectrometers mostly, to do spectroscopy. We use mainly the light sources available at DESY, the storage ring Petra 3 and the free electron lasers. And then what we do is we record electronic structure images and electronic structure movies, mostly using modalities of photoelectron spectroscopy, ARPAS in particular, and time-resolved ARPAS. And this is now the outline of my lecture, and it's really, I guess, a lecture style where I want to also give a little bit of motivation on the one hand, but also my thoughts on the charge density waves, give an introduction onto charge density wave physics, and then come to time domain classification scheme where we try to group the charge density waves. It's not one unique phenomenon, one universal explanation. There are many different types. And I want to group this in the time domain. And of course, all of this is a reflection of my own narrow worldview, and my own narrow worldview, my blog in New York City is charge density waves, transition metal dichalcogenites, and angular resolved photo emission spectroscopy. Okay, so here's my question. What has humanity produced in the greatest quantity, and in what quantity? Humans? Humans? No. Humans is only 8 billion. Yeah, wait, no, I think quantity, number. No, oh, come on. Here, 60 billion. Transistors, come on. And it's so amazing. I mean, this is the average growth rate. It's a 40% growth rate per year, and this is extraordinary. You don't find this in many other things. Yeah? So this is Moore's law, and this continued for about 75 years, doubling the number of transistors every 1.5 to 2 years. So, and in the end, this is a sketch where here the number is given, and you end up with about 10 to the 22 transistors that has been produced worldwide. Yeah? In 76 years. This is about 1 mole of transistors. Yeah? And compare this with evolution, so 10 to the 40 cells in 4 billion years. Yeah? So what if you extrapolate? This has the same slope, so we could end up with the same capacity as evolution. Okay, so this, of course, is a big footprint. I want to compare this 10 to the 22 transistors, and let's say a typical transistor size 100 by 100 nanometers is 100 square kilometers. What's the size of 100 square kilometers? Okay, it's 1% of Corsica, so maybe it's this little area here around Cargèse. But it's 100% of the city center of Paris. So this is about a 10 by 10 kilometer in size. And of course, this already tells you that if you spread it out, these things are incredibly small, but if you have a big number, you can have a big footprint. Yeah? But then again, I was saying that this is about a mole of transistors. A mole we typically associate with this, so a cube of material, and there's about 10 to the 23 atoms in this cube of silicon in this particular case, and this means there's room for improvement. Yeah? If in principle, as physicists, we would think we could get things smaller and not so spread out. But the more important footprint is, of course, this ecological grand challenge, energy, and so forth. So we are now also with this artificial intelligence, machine learning, and so then the energy needed for compute is severely growing. At the moment, if you take 10 to the 22 transistors and calculate about 10 to the 14 bit transitions per year, and it's incredibly small energy, 10 attojoule for switching a bit. It sounds small, but if you multiply it with a large number, you end up with 10 to the 19th joule per year. And this is currently it's about 2% of the global energy production. So there's still a gap. But if we continue with our informational meltdown, this will soon increase, and we will reach the amount of energy we produce per year solely for computing. And then the question is, do we want to do this? Okay, there's a grand challenge. So 10 attojoule is a small number, but there is still room for improvement, and then you try to think how you can improve it, this switching. So we search a new type of switch. And then we have always 3 fundamental questions. How fast is the switch? How efficient is the switch? And how does it work? What's the mechanism? And here, the first question, how fast? So Uwe has told us ultra fast is faster than fast. So you always have to have something, you can put this in relation. Yeah, and this is the cleaning solution of my wife's contact lenses. And there you find this word ultrafast. Ultrafast here for contact lenses is 1 hour. Or processus ultra rapide, 1 heure, 1 heure. Yeah? But look at this, and the Italians also, they call it ultra rapido, so ultra fast, only the Germans are a little bit more modest, so they call it complete cleaning time, yeah? So it's not ultra fast. Yeah, okay, but our reference is this thing here. This is the MOSFET, yeah? This is how it looks like, or looked like a couple of years ago, because now we have these FinFETs. And then you can ask, how fast are they these days? Okay, and this then is in engineering, it's switching of a transistor is simply charging the gate capacitance or the total capacitance of this device. The operation voltage is 0.7 volts, and then the typical current, and then you can calculate the time constant it takes to switch the transistor. It's only a picosecond, yeah? I thought, and then you have gigahertz frequencies, so picosecond is terahertz. So in principle, they can be operated faster, but the problem is, of course, dissipation of energy. But this is then our reference, ultra fast, faster than 1 picosecond. Then the other thing is how efficient, and of course you can cook an egg on your processor, and efficiency is the avoidance of unwanted excitations. You don't want to create heat with all the switching, and this you can also then calculate. So the charging and decharging of the capacitor is associated with capacitance times voltage squared, and this gives you the 10 attojoule at the moment that you have, and the 3 nanometer node technology. So this is iPhone 15. There is 3 nanometer node technology from TSMC in there, and this switches with 10 attojoules every bit. Okay, this was the second question, how efficient, and then how exactly does this work? So here, mechanisms can be very complicated. This is an illustration from Rube Goldberg, where a milkman grabs a bottle of milk, an empty bottle, and then there is a complicated mechanism where in the end this octopus squeezes this orange so that you can get a glass of orange. Okay, mechanisms can be complicated and they need not be universal. This will be a message I want to convey here. So what's the mechanism of a transistor? It's thermionic electron emission across a barrier. So here in the channel you have this band line up and you create this barrier, and here's your Fermi-Dirac distribution of electrons, and here the electrons in the tail, the hot electrons, can pass this barrier. This is how transistor switching works, and this is then associated here with this probability to lift something across this barrier, so this exponential rise, if you turn it around, of the ion current. But this is independent electrons, so every electron you lift across this barrier, and in the end, what these transistor people do, they calculate the slope. Yeah, so and they do it on this log 10 scale, and this at room temperature gives you this slope of your switching 60 millivolts per decade. Yeah, so, and how could you improve this? And one thing is that you switch between 2 different states, and they have an energy barrier. And in principle, we have seen that that the charging of this gate capacitor gives you this energy difference between off and on state. And here you have the large Q, yeah, which is at the moment about 100 electrons. So 100 electrons you need to charge a current transistor. Yeah? And this then, instead of this single charge, elementary charge, you have half of the large Q, 50 electrons. And this is why if you could switch collectively all your electrons, all the 50 electrons collectively, then you would have a much steeper curve. So this is here this slope. So this is this transistor curve, this 60 millivolts per decade. And you could come closer to this ideal switching where you don't have a finite slope, where you can have this vertical thing, and then you can go to low voltages and need very little to switch, little voltage, and this saves you a lot of energy. Okay, so this is the idea. Collective switching of electrons, maybe as a new switching mechanism. And this is also one thing people think about when they think about the future of the transistor. 3 nanometer node means we are approaching the end of this conventional scaling, and we need to think about new mechanisms and maybe new materials where also our transition metal dichalcogenides, 2D materials come into play, and a number of interesting mechanisms, for example, Mott transition or superconductivity. Yeah? So you have to think about possibly new switching mechanisms. And here then are the three important questions: how fast, how efficient, how exactly. So how fast? We want to be faster than this 1 picosecond. We want to go beyond simple drift diffusion of charge carriers. And ideally, we want to have an electronic switching, so a switching time that is sub-vibrational, faster than a phonon oscillation. And this brings us to the sub-100 femtosecond time scale. How efficient? We want to be sub-Boltzmann, go away from this individual lifting of electrons across barriers, and have steeper switching curves, so a slope below 60 millivolts per decade. And then how could one do this? Oh, okay, we are quantum materials people, so, and in quantum materials, electrons do a lot of interesting and potentially useful quantum things. So maybe we can realize correlated switching mechanisms that are much more energy efficient. We can be non-thermal, go beyond this Boltzmann regime. And then I take charge density waves as an archetypal electronic order, and I now want to explore the switching mechanisms, or the speed and the efficiency and the mechanism of switching charge density wave states in an ultra-fast way. Okay, and this brings me then to the second part, where I first want to introduce charge density waves again a little bit. You have heard a lot in the last week, and I will bring now all these concepts again, but I hope I don't bore you. So what is a charge density wave? And right from the beginning, we should point out that it's a trinity. Yeah? 3 characteristic properties, and one is the charge density modulation, which gives its name to charge density wave. So it's not a wave. Yeah? It's static. It's a static charge density modulation, which you can see in STM, for example, but also in XPS. So if you have differently charged atoms in your charge density wave, you can, for example, have a core level splitting. This leads then to the chemical shift and then split core levels. The second thing is, of course, the periodic lattice distortion, and this is typically studied in reciprocal space using diffraction techniques. Here, LEAD, low energy electron diffraction, and in this example, tantalum disulfide, this can be very complicated. It can have this Star of David-like periodic lattice distortion, but it can also have this stacking of different charge density layers in the 3rd dimension. So this can be very complicated patterns in real materials. And then the third signature, which is important when we want to use it as an electronic switch, is the energy gap. And also here, the gap structure can be very complicated. Gaps can appear at the Fermi level, but also at higher energies. So this means that in reality, charge density waves are not so simple as they may seem and as they are illustrated in textbooks. For example, using this simple chronic penny model which a simple-minded experimentalist like me can also deal with. So in this model, you can see it. You have attractive direct-com as potential, but this means that here you have not such a nice-looking sine wave, charge density wave, but still you have a periodic modulation of your charge density, and also your atoms are moved with the characteristic wavelengths here with double the periodicity. Yeah, and this Q vector, which corresponds to this wavelengths, you find in energy wave vector space, and this is this vector here, which connects your two Fermi points. Yeah, and if you have this modulation, then this can give rise to the opening of this energy gap, and this energy lowering of your electronic states here stabilizes the energy cost of moving atoms and bringing charge closer together in real space. Okay, so these are the passive terms. You have to move atoms from the equilibrium position. You have to act against Coulomb repulsion to bring electrons together. And this is the active term, which gives you this energy lowering. And if the total energy is below zero, you have stabilized this state. Okay, then what about this transition? So this is now the energy entropy argument. So this is the free energy. You have here energy, it should be below zero at t equals zero, and you have an entropy change between the two states, and this is also typically below zero. It's negative because phonons get stiffer, and the electronic structure, this gets gapped, and this leads to higher entropy. Yeah, and so this is negative. And if you go through zero with this free energy change at some temperature, then this indicates a transition. So these are the active terms. This is the thing which drives the charge density wave formation, and there we can now discriminate two different types of instability. One is the well-known Peierls instability, where you have a single electron picture, and this is mostly band energy gain, that by gapping you get band energy gain. But then you can also see this as an excitonic insulator instability, where you see it as a many-body problem, and where your exchange correlation energy and the change in that drives this type of transition. And another thing you can ask about this active term is, where does this energy gain come from? Does it come from the energies near the Fermi level? This is when you have a small gap opening, then everything happens near the Fermi level, and then you have a weak coupling charge density wave. But I've shown you in the case of tantalum disulfide, you can always also have a large energy gap, and the energy lowering can also happen at higher binding energies, large gaps, large splittings, and then you have a strong coupling charge density wave. And so you have two types of instability, and you have two types of charge density wave in a way. And here is the simple picture of the Peierls instability. So again, parabolic or a band dispersion here in energy wave vector space, a phonon dispersion in frequency wave vector Q space, and here our lattice and the charge density wave. You have this perfect nesting of the two Fermi points, and you already see this here in this little softening of this mode here at the relevant wave vector. If you lower the temperature, this instability, you have a logarithmic divergence, and this drives your phonon soft. When you have a soft phonon, you have a static distortion, and if you have a static distortion in your electron density and in your lattice, this gives you a new periodicity, and then you have opening of the gap at the Fermi vector. Yeah, and then again, if this energy gain is sufficient, then all this is stabilized. Then you have this other scenario, this excitonic insulator, and there you typically start or can start with an indirect semiconductor with a gap here, and then I do something experimentalists do, so I draw this exciton line, which is not a single particle thing, but I draw this in this single particle sketch. Yeah, so this is the exciton binding energy. It's smaller than the gap, but then through some mechanism you reduce the gap, e.g. it becomes smaller and you get to a situation where it's smaller than the binding energy of the excitons, and then you have spontaneous condensation or formation of excitons, and this drives your exciton mode soft here at this point, and the exciton hybridizes with the phonon, and a hybrid exciton-phonon mode goes soft. This leads then to, again, to a static distortion of the electron density and the lattice. And in the end, this new periodicity then also leads to the folding of the bands on top of each other, and the repulsion, hybridization, and the opening of the energy gap, and the energy stabilization. So these are the two types of instabilities. Then there are two types of charge density waves, strong coupling and weak coupling. Again, weak coupling where the gap is small and everything happens near the Fermi level. But here in this regime, the gap can get large, and then there's a continuous line going to even a chemical bond picture where the gap between these valence and conduction states is really, really large. Okay, and this you can then imagine in this way. So in a weak coupling charge density wave, the gap is small, and that means if you raise temperature, you can have electronic excitations across the gap, and this leads to electronic entropy, and electronic entropy then drives the transition to the normal state. In a strong coupling charge density wave, the gap is much larger than the thermal energy, so you cannot excite electrons across the gap. Instead, you excite phonons, and the lattice entropy drives the transition, and this transition then happens in two steps. So first, you destroy the long-range phase coherence. Yeah, you create domains. Yeah, and this is indicated through this diffuse intensity, for example, in diffraction patterns. And then in a second step, you also remove this short range order and do this undo your charge density and periodic lattice distortion. Yeah, so it's a two-step process, and it's driven by entropy, lattice entropy, and this will come again in the time domain. Okay, and then the microscopic origin. So this is a simple picture about the factors that drive the charge density wave. You have this susceptibility here. You have electron-phonon coupling. You have the phonon dispersion, and you have electron-electron interaction. Yeah. And so this non-interacting electronic susceptibility is typically written in this form, and it gives a peak at some wave vector, and this indicates the possible charge density wave vector. Then you have this term, which is really important. It's a structured electron-phonon coupling. So this depends on momenta, the Q of the phonons and the K of the electrons, and it depends on orbital. And then you have this electron interaction also included. So you have four factors that are relevant, and then you can say, okay, obviously to fulfill this equation here, this should be large, so that you have a small number on this side. This should be large because it's up here. This should be small, and this should be small. Yeah? And so then you can immediately already give three statements about charge density waves. You will never have a charge density wave without sufficiently strong electron-phonon coupling, because if this is zero, yeah, then this is negative, and then you can never be larger than this. Yeah? So you always need electron-phonon coupling. And there is no universal mechanism. You have these four factors, yeah, and they come together in different forms, in different materials. Yes, and you need to consider them precisely for every material you investigate. Nevertheless, people, Ward Plummer and co-workers in this paper, they have used this as a simple classification scheme. So type 1 charge density wave is driven by nesting or an instability of your Chi factor. Type 2 is electron-phonon coupling, and type 3 is what you do not understand. You lump into type type 3, and you'd say, oh, it's somewhat driven electronically. Okay, this is the table that they come up with. So the driving force is Fermi surface nesting, structured electron-phonon coupling, or electronic correlations. And here are typical materials which should correspond to these types of scenario. Yeah, and then you can look at what factors you find in these various materials. I want to give a little different time domain classification later, yeah? But just to mention that people have classified this, of course. And then one point I want to make, because there is these several factors, and how cool would it be if for some materials we would really make an effort to bring all the state-of-the-art methods together and try to solve this in a quantitative way. Yeah? So this is, in looking at these factors, is a qualitative scenario, but in principle you could calculate or even measure these different factors. For titanium diselenide, use latest state-of-the-art density functional theory. ARPIS, of course, gives you now very, very detailed images of band structures. Inelastic X-ray scattering or neutron scattering can give you all the information on the phonons. And other types of spectroscopies can really look into detail into these types of electronic interactions. And this would be really cool if an effort would be made to bring this all together and then try to quantitatively understand charge density wave formation, predict transition temperatures, and so forth. Okay, this is the end of my little introduction to charge density waves, and now comes a commercial break. We grow layered crystals in Kiel, transition metal dichalcogenides, the thinnest fish sandwiches from Kiel. So if you want one, send me an email. Okay, then now we come to this unordering. How do we want to do this? Come back to this thermal picture. Yeah, again, V-coupling, charge density wave, thermal excitation of electrons across the gap. And here in this strong coupling, you have lattice entropy. So electronic and lattice entropy, electronic and lattice disorder play an important role. If you do an optical excitation, we can always go above, excite electrons across the gap. So this is in a sense not critical. So we are always above. So we will have electronic and lattice entropy in these types of mechanisms. And then I'm interested in the electronic structure change, because again we want to use it as a switch, or could use it as a switch, and then we should look at the gap, which is then the measure of metallic or insulating behavior. And this transition then would evolve in a way, if you look at the gap, so in low temperature you have a sharp gap, you have coherent pairs, electron-hole pairs, so to say, you have a global distortion. Here, then you have, in this scenario, you have broken up long-range phase coherence. You will smear your gap because you have a local distortions. Your electron-hole pairs become incoherent, and then in the end, you don't have a gap anymore. So this is the cool thing. When we do ARPAS, we can really look at these things at the gap structure. We can see coherence in the form of sharp edges and peaks, and we can see incoherence in form of broad peaks and smeared edges, filled-in gaps, and so forth. Okay, and this now brings me to the third part, and now we want to undo a charge density wave, again, which involves three things: a gap, a modulation of the charge density, and a periodic lattice distortion. And then you can start to think, what are the fundamental time scales? Yeah, so you want to hit this thing with an optical pulse, with a short optical pulse. How fast can you destroy this type of order? Yeah, so for the charge density modulation, you need to move electrons from here to there, let's say. And what is the time scale of electron motion? It's the hopping time scale. H over your bandwidth, one electron, so this gives you a 4 femtoseconds time scale. If you want to undo the periodic lattice distortion, you have to move atoms, yeah? And there, the time scale, the relevant time scale is the energy of a phonon vibration, so 10 millivolt energy scale of phonons, so the oscillation period of a phonon is about 400 femtoseconds. And then if you think of the gap, What's the energy scale of the gap? The energy scale is 2 delta, and this transforms into a typical time scale. If you take 100 millivolt as a typical charge density wave gap, then this gives you 40 femtoseconds. And you already see that there are a number of different time scales, and then this gives rise to a multiplicity of processes, and so this can be complicated. And so ultimately, we of course want to be really, really fast and then look more into these electronic time scales. Okay, and then how can we look at this from a spectroscopic point of view? So my point would be, what is a charge density wave? It in essence contains 2 types of charge density. One electronic, which may derive from this excitonic insulator instability, and one lattice charge density, which is really tied to the atoms. Yeah? So if your atom moves, then your lattice charge density moves. So this you can split this up in the time domain. This will be a major point. And then if you look at the processes and the excitations involved in the destruction of such a state, then you find a lot of excitations inside your gap. You find the phonons, the acoustic and optical phonons. You find the excitations of the charge density wave, the amplitude mode, amplitudon, and the phazon, and you find other types of modes, amplitude phonons, phase phonons that couple to the gap. You maybe find a Flie carrier plasmons. So there's a lot of stuff, excitations going on inside the gap, and all of this you will somewhat probably excite when you hit your sample with this optical pulse. And then there are 3 ways to quench the gap. So closing, close the gap, this would be coherent motion. Filling, this would be an indicator of incoherence, so you do not move the gap edges, you just shuffle spectral weight inside here and fill the gap. And then you could also think, okay, maybe I have these peaks here, I just broaden them. So, and if you broaden these peaks, then you reach into the gap and also have spectral weight in here. So these are the 3 scenarios we will be looking at, mostly with time-resolved orbits. And the things, the excitations that are most relevant is the plasmon, phase phonons, and the amplitudon. Okay, and then now I give an overview of what will come. So I will have this matrix. So I will look at electron-dominated charge density waves, excitonic insulator type things, or phonon-dominated, the classical pi-earls. And then I will make a difference between a coherent displacive process where you have coherence in your system and let's say every atom moves the same way, or you have an order-disorder type transition indicated by the gap filling, and this is incoherent. Okay, and let's start with a simple scenario 1. So this conventional pi-earls instability. How do you undo your charge density wave? You have to remove the periodic lattice distortion, and this you do by displacive excitation of coherent phonons. You excite your system and you move this potential, and then all your atoms start to oscillate in this cosine type vibration. And so if you go to 0 displacement, and this is very well known, and people see this in the fraction. So you see these oscillations in the Bragg intensity of your superlattice peaks, and this is the frequency of the amplitude mode, and in this material here it's 600 femtoseconds. And then you excite your potential energy surface and you start to oscillate here at low fluence. At harder pumping, you drive the system into this type of form, not the double well potential, single well, and then you have this overshoot scenario. And this means here you want to go to this point here, 0. This is 0 amplitude. This is removal of the destruction. If you have this overshoot scenario, then you end up with a quarter period. So it's a quarter period it's the fastest time scale. Yeah? And here in this scenario, then this vibration of your atoms, it is directly linked to the vibration of the gap. As you can see in time-resolved ORPIS, you see these oscillations here. So here you have clearly a gap closing, coherent closes due to the vibration of the atoms, and the charge density and electronic structure changes are intimately tied to your lattice motion, to the amplitude of your lattice. This has very nicely been seen, this correlation studied by Martin Wolf and Laurenz Rettich in this study on terbium tritelluride, another important charge density wave reference material, where they have combined ORPIS and X-ray diffraction, yeah, for one material. And then in ORPIS, you see again the charge density wave gap, and you see then if you measure intensity characteristics, intensity, backfolded intensity here, or intensity inside the gap, you really see how the gap is quenched and how the gap is coherently closed again on a relevant time scale given by the period of the amplitude mode frequency. And in time-resolved X-ray diffraction, you see the same transients in a way, and these are perfectly correlated, and this again indicates that the time scale of the gap closing is connected to the time scale of the amplitude mode vibration, so there's nothing else, and it's a coherent process, and it can be as fast, so they have measured the time scale as 1/4 oscillation period of this characteristic period of the characteristic phonon mode. Okay, here again, they have also illustrated this in a nice dynamic energy landscape picture. You do the excitation. If you end up with the double well potential still in your excited state, you will have some oscillation in this shifted potential. Or if you pump hard, you can really undo the lattice distortion excited here, and then you go to here, and now imagine a strongly damped oscillation, and you end up here, and this would be 1/4 oscillation period. This is the fastest time scale. Yes, so he has really looked at it at the long term. So people then focus on the relaxation dynamics. So there are interesting things happening, and then you can also end up in these hidden states and so forth. But I'm not interested in these relaxation dynamics. Sorry, I'm interested in the switch, and I want to explore how fast. Yeah. You can really switch over. Yeah. So here again, just to illustrate this again in a clearer picture, maybe you start here. The order parameter is here, and then it vibrates in this higher state, and again it's 1/4 oscillation period in this overshoot regime. So then it can be a little bit more complicated. So in these materials, in the one-dimensional, quasi-one-dimensional charge density waves materials, you also have these phase and amplitude phonons which couple to the gap. And so you can also excite those, and these phase phonons in particular, they can really smear the gap. Yeah, you now introduce incoherence in the system, and the measure is that you relate the energy scale for electron phonon scattering. So here and put it in relation to the gap size. And if you have strong electron phonon scattering, you can imagine that you will smear the gap and fill in spectral weight in the gap. And this type of order parameter is very large for these types of systems. And in our time-resolved ORPIS study by Lexian Young in the group of Michael Bauer and myself, we have studied at this and looked at the gap here, the charge density wave gap here, which is not so clearly visible because the energy resolution is not high. Then you go to difference, ARPIS map, and what you see is red is added intensity, and blue is removed intensity, and here in between you have the gap. And then you see how red enters into the gap region, yeah, on a time scale which is relatively fast. So this line here is half of the oscillation period of the relevant phonon, and this gap filling in, intensity filling into the gap, is much faster than this coherent process. Yeah, so then you can integrate the intensities, and then you can really see, this is a blue transient here, how the intensity in the gap rises on a time scale which is much faster than this thing here, which is due, that's the first maximum of the oscillation, the coherent oscillation. So here you really have a scenario where you can quench a gap by filling it in much faster than the coherent vibration. So this is then an order-disorder type transition happening on a characteristic time scale of these phase phonon modes, which again have higher energy than the amplitude mode and thereby shorter times. Yeah. Okay, here again we have that the charge density is mostly given by the lattice charge density, but now we start to vibrate this lattice in a fast way and thereby introduce incoherence in the system and fill the gap. Okay, and there is then a relation to this VO2 where you have the dimers and where Simon Wall has studied this with ultrafast X-ray diffraction, and where he also made the point that on the very fastest time scale and on that strong pumping, this is not a coherent displacive transition where all the atoms move coherently, but it's an order-disorder transformation, which you can see in the experiment through the occurrence of the diffuse intensity. Diffuse intensity, again, indication of breaking of long-range coherence. Yeah? And they, again, then see in the experiment, they see the extended areas of diffuse intensity occurring, at a very fast time scale. So this here is the relevant intensity transient of the Bragg peaks, and here you see the occurrence of the diffuse intensity happening on a very fast time scale, which corresponds to about half an oscillation period of the relevant phonon mode, which in this case is this 3 terahertz mode. So this is a little bit different from this multi-phonon phazon disordering. This is due to two things. For one, that you have the very flat acoustic phonon dispersion here, low energy modes in an extended region of the Brillouin zone. So this will give you large entropy. You're susceptible to phonon disorder. And then you have this flat photoexcited potential where in principle, so the frequency, which is related to the curvature, would be very low. But here, you do not have this coherent displacive excitation. Here, you would start out with inertial motion. Yeah? So the thermal velocity of your vanadium atoms at 300 K is 3.8 angstrom per picoseconds, and this is the distance you have to bridge, and 0.24 angstrom. So this can happen in sub 100 femtoseconds. So here you have an initial velocity. You do not start in this cosine thing of the coherent displace. You start with velocity 0. Here you have inertial motion through this flat potential, and then you have this disorder type transition, order-disorder type transition. It's slightly different from the one I mentioned in the Leblanc system. Okay, and then type 3 then is finally this excitonic type instability, where again here so far everything was tied to the lattice charge density. Here now we can really have the separation where we also have an electron charge density, and where in principle in the time domain we can split these things. So people have also illustrated in this way, so that we have an order parameter, and this has two contributions, one coming from this excitonic insulator instability and one from the Peierls instability. Yeah, and this has been also demonstrated already in terahertz spectroscopy. So you can have, in this scenario, a state where you can quench this electronic component very fast. So this is indicated here at a critical fluence. You have the scattering rates of the normal phase. So you have quenched a specific electronic correlated state, have quenched the electronic correlations, but still you see the relevant phonon mode. So the lattice distortion is still there. Yeah, so quenched electronic distortions, persistent lattice distortion. This you can have the split scenario in this excitonic insulator instability, and these results are a strong indicator that this is really true. And then there's this very recent publication from Klaus Roper's group in Göttingen, where they have measured this using ultra-fast lead, and where they have weighed the contributions in a way, lattice versus excitonic, by looking at the superlattice diffraction peak, where they have looked at the response of this peak, and where they see that the intensity of this superlattice Bragg peak is quenched very fast, quenched by about 30%, and then it is persistent. And then this corresponds to this periodic lattice distortion, which is persistent, while 30% of this ordered state is quenched. So fast electronic quenching persistent lattice distortion. And then you can ask about the time scales. Now you should find both time scales, and indeed, using ultra-fast X-ray diffraction, you again find this quarter or half oscillation period from the coherent phonon displacement. And this is what we have done together with Michael Bauer in the electronic measurement. You find this very fast quenching of the backfolded bands, which is the electronic superlattice peak, so to say. Yeah, and this response has a characteristic fluence dependence. The harder you pump, the faster you go. And if you scale this, you find that this corresponds to a square root dependence of the electron density. And this is indicative of a plasmon type excitation. So here you find then the plasmon time scale in this type of scenario. And if you bring the time scales together, you can see at strong high fluences, you have this electronic dominated processes. At lower fluences, it becomes phonon dominated. And then here you have a gap closing happening on multiple time scales, fast electronic component and a slow lattice component. And here, this is then the unique case where the charge density wave really is two things in one electronic thing and one lattice thing, and not everything is directly tied to the lattice. So here is how, yeah? It's the free carrier screening. So you have a plasmon, you create free carrier plasmon, and it's free carrier to create the hot electrons, and they screen the interactions. Yeah. Yeah, so I imagine it in this way. So here you have the gap, and here you would, let's say, Thomas Fermi type screening with this screening wave vector Ks. Ks is proportional to electron density, 1/3, and electron density is proportional to plasma frequency squared. So this in a sense, yeah. And then the time scale is then given by the plasma. So you go from here to here, and you go in a way coherently because you screen everywhere in your material. And this is the experiment where I've directly seen, using Robert Huber, where they've directly seen these plasmon-type excitations. So this is a free carrier plasmon at 45 millielectron volts. If you do the hot electron excitation, you shift the plasmon energy to the right. If you do strong excitation, far to the right, and so you have direct measure here via the plasmon frequency of your charge carrier density that does the screening. Okay. Here then is my my table of the 3 types. Different types of stabilization, different types of transitions, so either coherent displacive or incoherent order disorder, different time scales, all put in different mechanisms and driving forces of these ultra-fast transitions. And now I see that I should... Yes. Yes, but in these materials, they are more metallic than this than titanium diselenide. And there, the plasma frequencies are on a very higher energy scale, let's say 1 electron volt or more. And then your excitation doesn't change that so much. Here in this titanium diselenide, in the excitonic insulator business, I mean, you see it directly, the plasmon, the free carrier plasmon is really, has low energy, yeah? Because the charge carrier density is low from the beginning. You start out with a near semiconducting picture because you have or only small band overlap or a small gap. Yeah? Whereas in the more conventional charge density wave systems, they are more metallic, and the charge density is much higher, and you do not change much. Is it? Okay, then I argue as an experimentalist, I do not find this time scale in the experiment. So I see it's not relevant. And it does not match this. Yeah. Yeah. But then, let's say in my little picture where I say, okay, this is a case where the charge density wave is intimately tied to the lattice distortion. And then how would a plasmon undo this lattice distortion? Yeah. Okay, maybe I can stick with my experimentalist point of view. I don't see the time scale in the experiment. Okay, I was running out of time. So there are, of course, other types of electronic order spin density waves, so purely electronic, and mod insulator. There are more than electronic time scales. Yeah, I know, I have to come to an end. There are the superconductors. Yeah, superconductors, you have to break the Cooper pairs to close the gap. Yeah, you do the electronic excitation. The electrons have to transfer their energy to the 2 delta phonons, which break the Cooper pairs, and this then leads to the removal of the gap. Okay, this you already see. This is an indirect process. Takes probably longer time than in a charge density wave. Yeah, people have measured this, and then you can see this to really quench the gap size. It's in BCS type superconductors. It takes more than a picosecond to get rid of the electronic order. In cuprates, it's a little bit different because there again you have these phase fluctuations, and people have argued that by exciting those, you can fill in the gap. Again, here you nicely see in ARPAS how you fill in the gap. Yeah, so the peaks stay more or less at the same position, but you quench the gap by filling it. Yeah? And this can be a little bit faster because these phase fluctuations have a 15 millivolt energy scale, which corresponds to a time scale of 280 femtoseconds, and this then is this time scale of quenching the gap. And if you then bring all together, here these various systems, here's the gap size, and here are the time scales. Yeah, and then you find here the indirect, incoherent processes in the superconductors on the left side. Yeah, at rather slow times, far away from this fundamental scale of the energies of the gap and the corresponding time scale. Whereas in the charge density waves, in particular, when you think of these phase phonons or the electronic screening mechanism, you can approach the fastest time scale. So if you think of a switch, you should go for a charge density wave system. And here again, this illustration, the excitation path, hot electrons, different mechanisms, and these can be fast or slow. Okay, and then I should finally come to the efficiency thing here. I compare the efficiency of switching. And one measure, and this was also done by Dragan Mihailovic in this very early paper, where they have compared the condensation energy of your charge density wave or superconducting state, which is related to the density of states at the Fermi level, and the gap size, and compared it to the energy that you deposit by optical excitation in your system, what they call the vaporization energy. Yeah, and here again for our systems, and here's this condensation line with some error bars because I do not find so reliable values for the density of states. Here again, the superconductors are inefficient. You have to put a lot more energy in because you have this indirect process, dissipative process, whereas in the charge density waves, via these coherent oscillations or via the electronic screening, you are relatively efficient in killing the charge density wave state. So in the end, if you want to do a charge density wave switch, of course, here's my little caveat. Yeah, it should operate at liquid nitrogen temperature, which is not so good. But let's say for conceptually, yeah, so the switching energy would be this condensation energy. If I go with a 2D system and take the 2D, the density of states of the 2D electron gas here, and if I go with a mean field type transition with 300 Kelvin transition temperature, this is the gap size. This would give us 53 millivolts switching energy and a time scale of 46 femtoseconds. And I would say you need about 15 atoms square so that you have a developed band structure, 15 unit cells, and maybe you can speak of something like a band. Okay, this you can compare to current technology, switching energy, 10 attojoule. This sounds low, but it corresponds to 62 electron volts, and this is huge compared to this. Switching time is also longer, and at the moment you have a volume of this fin in your FinFET of about 4,000 nanometer to this cube. And this is the fundamental limit. Yeah? So Shannon von Neumann-Landauer limit. To switch a bit at room temperature, you need 18 millivolts. This would correspond to 37 femtoseconds and a minimum size of 1.5 nanometers. So at least conceptually, we are not so far away from this. But of course, this will never happen. You will never have a charge density switch. It was just a conceptual idea. Okay, and this would be the summary of these different ultrafast and ordering mechanisms and energy timescales. So this is my matrix. Electron-dominated processes, phonon-dominated, coherent, incoherent, and there are a number of excitations relevant in the destruction, and I have a couple of open challenges. So I really want to go ultra fast on the electronic timescales. So this fundamental timescale of electron hopping. It has not yet been resolved in the experiment. Yeah? And also, we have always looked at these coherent phonon vibrations. This you can easily see in electronic structure. But I would like, for example, in a spin density wave, or in possibly in this titanium diselenide, where you have this electronic component, I want to see a coherent electron oscillation on the fundamental time scale given by the gap size. And if I see those, then I also want to see it together with a coherent oscillation of the phonons, and then maybe see some interaction effects. Okay, I would have a little bit of outlook, but I should stop now, or? Okay, I want to offend the theorists. Sorry, or I don't want to do it. Scientific revolutions are more often driven by new tools than by new concepts. So this is what Freeman Dyson says. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have to be explained. So, okay, this is from an experimental point of view. Just one thing. So concepts are very, very important. I'm not saying anything against. We have seen these energy landscapes over and over in the talk. These things now become quantitative, and this is very nice, and I think they really provide an intuitive way of navigating this free energy landscape and maybe visualizing a little bit these transitions that are complicated. And then there is this role of disorder. I think this can be or is important. I try to show you that this incoherent stuff also can play a role in gap melting processes. And so this is what people then called correlated disorder, somewhere in between order, perfect order, and fully random disorder. Yeah, okay, then I would talk about a few more experimental developments, which I really like. But in the end, I want to advertise this. So we have looked at electron and lattice dynamics using different techniques, ORPES, time-resolved ORPES, time-resolved X-ray diffraction, ultrafast lead, and so forth. How about combining this in a single experiment? And here, photoelectron spectroscopy can be a cool tool because there are different modalities of photoelectron diffraction. One we all know, and this is ORPES for band structure mapping. But if you look at the core levels, you can also do photoelectron diffraction and thereby get information on the lattice and its dynamics. And we want to combine this in a single instrument. We need soft X-rays because we want to excite the core levels, and that's why you find us at soft X-ray free electron lasers, at Flash in Hamburg, at European X-FEL in Schenefeld, and of course we want to then go to the brightest or highest rep rate facility, and this will be LCLS2 in Stanford, where we will ultimately, hopefully, have 1 megahertz repetition rate, and there we can really then do systematic studies of combined electron lattice dynamics. Thank you for your attention.